before this multiple qubit, I will be discussing some basic concepts of linear algebra. Like Boolean algebra plays the role for classical bits, same role linear algebra plays for quantum computing. Or in a simple way, what is the importance of Boolean algebra in classical computers? The same importance linear algebra hold for quantum computers. Okay, so for the gate, we have I told you it should satisfy two property. The first it should be linear, that means it should able to distribute to the superposition, and the total probability must be 1. What does it says? That after applying it should result in a valid qubit, that should not generate anything other than this. Okay, now let's go for some of the quantum gates. So first gate is classical reversible gate, and we all know classical reversible gate not was that classical reversible, or simply it transform bit 1 to 0 and this 0 to 1. Got it? Simply if we talk about qubit, if we talk about a qubit, then the classical gate reversible gate for the qubit will be, it will transform the 0 in 1 and it will transform the 1 to 0, acting on the superposition. Suppose my initial qubit is this. So if I apply this gate on the superposition thing, what I will be getting, it will be getting by this 0 will be changed to 1. So it is satisfying two properties. First, it is applied on superposition, and simply I could write it like this. The probability also remains to same. So that means yes, reversible gate exists. So classical reversible gate, that means the gate which reverse the qubit, is a valid quantum gate. So in a simple way, if I say classical reversible logic gates are valid quantum gates. So whichever gates are reversible, they are valid quantum gates. Let's take an example of irreversible gates. Suppose there is a gate in a classical system which is not reversing, it is changing to 0 to 0 and 1 to 0. So if I use the same gate for the qubit, so when I try to apply it on the superposition, it will be alpha 0 plus beta 0, which is alpha plus 0. Okay. Now let's see the second rule. Probability should be sum. So now alpha plus beta square, which is equal to so it turns to alpha alpha star beta beta star alpha star beta plus. This we know it's alpha square plus beta square. So it is 1 plus, sorry. and this is definitely not equal to 1. So that means it is not a valid quantum gate because it is not satisfying both the property of valid quantum. So in a simple way we can say all the classical gates which are reversible, they are valid quantum gate, but the irreversible are not. You have to check the property, they are not or they may not be a valid, but this is damn sure if the classical gate is reversible, then it is a valid quantum gate. And this is one of the question also you can try whether they are valid or not. 0 1 1 1 first, and the second one is which of them is a valid quantum gate. And simply we can expand the question like this also. That means it will, the classical logical gate is taking the input A and B and giving the output as C and D. So which of them will be a valid quantum gate? These are all these questions are for the given tables are the table for classic logic gates. The question is which of them are valid quantum gates. One I'm just making you to do. How will you check it? The same concept, apply it on the superposition. At least try on this first and second question.
Ma'am, first is irreversible, second is reversible.
First is reversible, second is not reversible. Yes.
Ma'am, first is not reversible, second one is reversible because unique mapping we can
Yes,
use.
yes, yes. Actually, I was seeing from the book. I was just okay. Yes, this is not reversible, while this is reversible. How will we doing for the two gates?
I think we should try for each
Yes, we
one
have to try for
mapping.
each. This you try. This is the today's assignment. If simple this question you tried, and remind me tomorrow I will be discussing the same. So this is I'm just giving you one assignment for this. Okay. So this is a simple way we can check
Ma'am, there is
which.
one question.
Huh?
Ma'am, we can actually use the unique mapping technique to check in classical computing that it is reversible or not. So my thesis is that if it's not reversible in classical, then it is surely not reversible in quantum, in qubit.
Yes, if it is irreversible in classic, then it is not revert that then it is not a valid quantum gate.
Yes, ma'am.
Huh. That is the thing that we see. Simply to define to define the quantum gates, we require two property. Now we are transforming classical gates to quantum gates. Then we check for the gates which are reversible. That we can map to quantum gates. If they are not reversible, we cannot have them as a valid quantum gate. So that means these operations are not possible to perform using quantum gates. Or simple way of saying this like this. Okay. So let's start with some of the common one-bit quantum gates. The first gate is simply we write it as I. Identity gate one, so it simply does not change the bit. It is a valid quantum gate because see, it will work on the superposition and it is not changing. That means whatever is the qubit before applying the gate, it is the same one. So simply if I say, so the rule will be satisfied. So it's a valid quantum gate. The second gate is poly X gate, or we also call it as NOT gate. It's like the symbol we use it X. It is simple like NOT gate in the classical 1 to 0. Classical, it was reversing the bit, while in the quantum, what it is doing, it is rotating about X axis. So simply, you remember 0 was standing for North Pole, you moved it to South Pole. When it was South Pole, you moved it to South. Now what will happen? If the bases are plus and minus and we use this X gate, in X, if you rotate it with respect to this plus and minus, it will have no change. So simply and when you rotate any point on the y-axis, this will also get rotated. So rotation about x-axis by 180 degree. Okay. X square is equal to identity. You apply X gate twice, that means you are rotating about 360 degree, then it will be coming to original. Now suppose you have to find out what will be X 1000. Simply we could say it is X square to the power 500, so which is equal to identity. So simply if it is given in some this form exponential sum, you can simply simplify it, then we can apply the quantum gate. This poly X gate, if you see, it's a classical gate also, because what it is doing, it is transforming 0 to 1, 1 to 0, like your NOT gate. So this is a classical gate also, 0. Next, when we talk about Y gate, this is not a classical gate. What it does, It simply just wait a minute. Hello, hello. हाँ बेटा ओके बेटा मैं तेरे को 10 ढाई घंटे में फोन करूँ मैं क्लास ले रही हूँ ओके बेटा so this transform 0 qubit into 1 1 into 0 in this basis. Now you can see it is using the complex numbers which was not present in the classic gate. That is why we say it's not a classic gate. Now let's check whether it satisfied a quantum gate property or not. So first, if I apply it on the superposition, it will be alpha so simply it is alpha or iota alpha 1 minus iota beta 0, okay, plus iota. So superposition this property. So if I do so it will be the conjugate is minus alpha beta into 2 minus alpha. So it will be beta square plus L quantum gate. It's a y rotation vibration about this also follows the same thing. Poly Z gates. This is also not a classical gate, and what it does, but it is also a valid quantum. Okay. Now let's do some questions also for this. Now suppose you have, and the same rule it also follow, z square is equal to identity. I'm giving you a question. Suppose you have to perform Z217 X
Excuse me, ma'am. Ma'am, your voice is breaking.
alpha 0, what will be the result? Mm, I will just x is simply, if you okay not able to, I will write the x for you. See, z is front of you, x I will just write for you, and x also satisfy this property. Now, Hanji, my voice is gonna, should I reconnect again? Should I reconnect it if it is no one is able to hear me properly?
Yes, ma'am. Please
No
reconnect.
response. I have just checked it. Just tell me. Is it now improved? Are you able to now hear properly?
Yes, ma'am.
Yes, students. Now, are you able to hear now properly? Okay. Again, I've just rejoined it. Now tell me, is the voice now clear?
Yes, ma'am.
Yes, ma'am.
Okay. So let's come back. So I've discussed you three gates, three poly gates X, Y, and Z. They simply rotate the qubit around, first X gate rotate around X axis, Y around Y axis, and Z around Y axis. And if you apply this gate twice, it is equivalent to identity. So now the question is, the question I've written in front of you. Now tell me what will be the result when I apply this on this given bit.
I mean, in place of beta, it will be minus beta.
Yes, it will be alpha
Ma'am, your
0
voice is breaking again.
minus beta. Because see, x to the power 50 will be identity and 212 will be identity. Now it is only single z. Okay. So simply this is equal to identity, this thing. Now also it's breaking.
Yes, ma'am.
Mhm. How will I take the class? Okay, try this.
Ma'am, your voice is lagging too much.
Okay, I am not speaking. First of all, you do this question. I will reconnect again. There is some problem going with the network. I will be switching to some other place. Wait a minute. इसको बंद कर दो. Just check student whether the lacking is over or not. Is the quality improved?
Yes, ma'am.
Now just to do this question.
Yes, ma'am. Done.
Done? Proved?
Yes, ma'am.
Okay. Now next gate is phase gate. What is, or we can simply say it as gate also. Simply it is a rotation about z axis by 90 degree. So this is how it transform. Your s square is equal to z, because s into s, now the rotation will be 180, and simply s4 is equal to identity. T gate, it is also called as pi by 8 gate, like phase gate is also called as pi by 4 gate. Pi by 4, 360, yes, 90. It's also called as pi by 8 gate, and simply t square is equal to s, and what it does,
Ma'am, can you explain P gate again?
hmm, P is phase gate. See, the previous x, y, z were rotation about the on x axis, y axis, or z axis. When I talk about the phase gate, it is also rotation about z axis, but now just it's not possible for me to show in the video form. Now just think, if I talk about a Bloch sphere, have a look of this. Hmm. Now see this we consider as z-axis. Any point you are rotating, that means initially what were you doing? Whichever point was here was coming to this point, and the point which was at this was coming on the this. This was the swap happening. That means after the rotation, star was coming here and this was here. Now what is happening? They are coming in a rotation. But any point, simply if you think, they are just, the angle is not 180, they will be in on the different sides of side of the sphere, large sphere. Rotation will be 90-degree. You just take 3 pens and orient the direction and then put a pen on the north and south pole. You will be just seeing it. What happens? Simply zero will go on the x-axis, and this one dimension point will come on the y-axis. Now you can have a feel also. Just see, this was this location star, and this was having when we are having 180-degree. Now when we are having 90-degree, just see the point, this will land here and this will land here. Okay, now see the coordinates. Got the idea? The point which was on
Yes,
x-axis,
ma'am.
0, that north pole, the x-axis, and which was on the south pole, it is on the y-axis. And see the coordinates are mapping on like this. Clear?
Yes, ma'am.
I tried to explain because it is at some 3D. So I tried to explain. You can just take 3 pens and just draw it and just check it. If it's possible, not, then I will explain it. Okay. So this is like, these were two. These are gates were designed. Simply, you could have rotation, or the gate can be designed with any of the axes. Like simply, there was a gate R Z theta. What it does, which these S, T, P, X, Y, these all are standard gate. This I'm just taking in general because this were taken. They are normally used in this, the current work going in quantum. So when you are going with pi by 2, pi by 4, can we have a general gate? So this is one of the example I'm giving you. Yes, you can have. Suppose this RZ rotate about Z axis by angle theta. So RZ, it will be no change. So generalized form, we could write it like this. So this is a generalized form, you can write it. And this you can check by substituting all the values of theta, that this is a generalized. So simply your Z gate is RZ with the angle pi. Your S gate is RZ with the angle pi by 2. And your T gate is RZ with the angle pi by 4. Similarly, you can design it for any angle. Okay, now next is
Ma'am,
very
excuse me.
important.
Ma'am, how does it affect on x-axis and y, ma'am?
How does the movement changes on? Simply now, this you I will just, I can show it, but I am giving you one just to do it. You can represent 0 and 1 in the basis of plus and minus. In the last class we discussed.
Yes, ma'am.
So try to do that conversion. Simply represent these plus and minus in the form of 0 and 1, and then apply 0, 1 on that gate, and whatever is the result will be the value of plus and minus. Got an idea how will we do it?
Yes, ma'am.
Similarly, you can do for iota and minus iota also. Represent them in the 0, 1 basis and then apply the gate. That's why we are discussing on the generalized 0, 1, because we all know how the conversion works. So simply convert them bits in the 0, 1 notation and then apply the gate. This is how we will be doing for any of the bases. Clear?
Okay, ma'am.
That is simply done in the classic computer only. We do it for the simple bits 0 and 1, then we can apply for any number of bits or any representation and all. So same concept is there. We are discussing on one basis, and you know the conversion. Now you can do it on any basis, not on x, y, z, on any of the base notation we can do it. Okay, the next gate is Hadamard gate. Pronunciation of these gates, poly is the simple, but these gates, I'm you might, because in many of the universities some you might be hearing different. Normally it's called as Hadamard gate only. So what it does, this is a very important gate. We'll be using it in many problems. So simply, if what it turns, huh, it turns 0 to this, and hmm, so it transform 0 into this plus x-axis basis and 1 to, it changed the basis, and this is also a valid quantum gate. Now let's check whether so 0 and 1 simply it transformed to this. Now what about other bases? Let's have a look. So how we represent plus? We represent it with this. Okay. So simply that's why I'm showing you one of the apply methods you can understand. Now had this is equal to this, so it will be 1 upon root 2 0 plus 1. So when I solve it, simply it is equal to 0. So same, it will be 1 upon root 2. If you apply it, 0 minus 1 upon root 2 minus 1. And when you are going to solve it, you will be getting it value as 1. Similarly, you can also try for this. This I am leaving as an exercise. No, this you will be stuck. I will be just solving you for this because it is 1 upon root 2 0 plus iota 1. So which is equal to 1 upon 2 and if I solve it, 1 upon root 2, it will be 1 upon root 2 plus iota root 2. So when you solve it, 1 upon root 2 here, the 0 coefficients are here, so it will be 1 plus iota root 2 0 1. Is it clear? If you write in a polar form, you can further write it on in a simple form, e iota pi 3 or simply this conversion, how I have done it, because see 1 upon root 2 is pi by 4, and simply x square plus y square is 1. So this is how I have taken it. And minus, so simple the angle will be 135. So it will be minus iota by 4. So this is just for the information and further to represent in the polar form. If you are understood, it's okay. Otherwise, this will be how the conversion Hadamard gate will work on the this plus if the representation in the on the y basis. Is it clear to all? So this one part is optional. And suppose I think all of you have now got an idea that you can apply any of the gate on any of the bases in the similar manner. I have applied this Hadamard gate on all the bases. Is it clear now? So this one question I'm giving you. Now this is a combination of gates. What will be the answer for this? Let us do this one. Just doing for one bit. What it will do? I was to write here TH first. Or let us simply let us make it first a simple one. H rotation by pi by 8, then S gate rotation by pi by 2, and then again a Hadamard gate. Is it clear? And that after these gate, this will be our resulting qubit. Is this clear?
Ma'am,
Yes.
I mean the first step we apply root 2 on 0 vector, but we not in
Really,
1.
both. I will just keep this root out so that you get an idea. This is this.
Okay, ma'am. Okay.
It is like this. That's why in the whole this one is this. Okay.
Yes, ma'am.
Okay. I will give you some one question also, so you get more clarity of this. So I'm giving you two questions. First is calculate. Okay, one more thing is left on my side. And the important thing is, see, Hadamard gate has also this property. You can write it here also. In Hadamard gate also, h is square is equal to identity. It changes the plane, but the moment you apply this gate also twice, it will also result in an identity. So the question is apply y99, t36, z25. First question is this, and the second question I'm giving to you is calculate
Ma'am, what is the power of y?
51. Hmm.
Mhm. Ma'am, solving from the left to right and right to left gives the same answer, ma'am.
You have to do it like this. See, first of all, Z gate will be applied, then T gate, then H gate, then I gate. You have to move from right to left.
Okay, ma'am.
So these two questions also you try it, and tomorrow will be. You remind me of these are four questions I have given you. Tomorrow I will be discussing, and tomorrow I will give the solution also. This. Now last thing in this, because I have done.
Excuse me, ma'am.
Hanji bacha.
Can you, ma'am, please write the answers only so that we can verify our solution?
Answers of them.
Yes, ma'am, so that we can verify later on. Otherwise, no problem if you can also do in next class as well.
No, I will be writing the next class because till that point you try it.
No, no, ma'am, just only a solution, final solution, so that we can verify our answer. Is it correct or not?
Okay, I'm writing that. For the first one, your answer will be minus iota okay, and this the answer will be 1 upon 2 root 2 1 minus iota plus 2 iota Okay, so this will be the answer of your both questions. Now, as you draw a circuit diagram in the classical, similarly, circuit diagram can be drawn in the quantum also, and we call these circuit diagrams as quantum circuit diagrams. And this is nothing just to show how the gates are applied. For example, if it is SHTH and I am applying on this, I will be writing it as 0. The first gate I have applied is H. The way you are doing the processing the same way. That means in this order. S and then H. Sometime in the books or in the version you will be also seeing the output. They show it like this. So simply it is last we call it as a meter. That means now it will be showing a position of the quantum bit on the sphere. This is not because the simulation and the coding is not in your course. So this is a simulator tool available, web-based tool. It is simple, where you can simulate the quantum bits, because see single bits or simulation for a number of for the initial number of bits is possible for classical system. And if you have just gone to the net and you have seen 20-bit IBM quantum computer is taking how much big space. Google, I suppose, has gone for just 20 quantum bits, and IBM has said that he succeeded in 32 quantum bits. This is the level of work till now. I suppose in the last year only Google announced for 20 bits, and the size is like the initial years we were having our computers, a big room size computers. So this is the current size of quantum computers. And in this course, as you will proceed, I will tell you why it's because it's again going a challenging or it is a research field. So but this is a basic simulator tool where you can check it for 1 bit all available. Is it clear? So today I will be winding it with the gates. In the next class we will be starting with linear algebra, the same rule that Boolean algebra plays. So can I take the class tomorrow or on Monday?